So in the previous videos, we've been talking about compound interest and the different compounds that we can have. Compounded annually, semi-annually, quarterly, monthly, weekly, daily. But there's another type of compound to where it's a continuous compound, right? Every minute, every second, you can be accumulating the interest, and that interest is deposited continuously into your account, not just at the end of a week or a month. Just continuously. Each time you earn, say, a penny in interest, it puts it in there. And so it's that continuous compound interest. And the more times the interest is deposited into your account, the more money that you can make, right? Because you're earning interest on that interest. So the more times the interest is deposited, the more money that you're making off the same principal that you have. All right, so this continuous compound interest, since you have an infinite number of compounds, M would be considered to be infinite, we cannot use that same formula that we use for the compound interest. So we need to derive a different formula for this. And on the screen here, we see what this would look like if we let the number of compounds grow without bound. In other words, if we let M go to infinity, then this leads us to the following formula. Now there's some steps here to get to that final formula. I wouldn't ask you that on a test or anything, but it's good to know, right? So this is the regular compound interest right here. A equals P times 1 plus R over M times raised to the M times T. Right, so if we let U equal M over R, right, if we let U equal M over R, then R over M would become 1 over U. And if we took this U equal M over R and we solved for M, that would give us UR. So we could replace this M with UR, and it gives us this next line. A equals P times 1 plus 1 over U raised to the UR times T. And then by regrouping here, if we were to take this 1 plus 1 over U raised to the U and then raise it to the RT, right, then it gives us this line. And common knowledge, not really common knowledge, but in the math world, 1 plus 1 over U to the U is kind of like a calculus thing. As the limit of this, as U goes to infinity, right? As M goes to infinity, U will go to infinity. This 1 plus 1 over U to the U, that will approach E, right? We had said in the previous video, E is what's referred to as Euler's number. It's an irrational number, 2.71828, but it keeps going. It's an irrational number, similar to pi. All right, so we have A equals P times E to the RT, right? So this is the formula that we get when we let M go to infinity. This is the formula that you will need to know and know how to use. Let's look at an example on using this A equal P times E to the RT formula. This is when we have a continuous compound interest. For example, find the accumulated amount after 6 years if $6,500 is invested at 5% per year, compounded continuously. All right, so we see this compounded continuously. That's telling us that we're going to use this formula A equal P times E to the RT. So let's identify the variables. All right, E is not a variable, E is a number. All right, there is a button on the calculator that you can use for that. All right, so find the accumulated amount of an initial investment of $6,500 with an interest rate of 5% over 6 years. Okay, so now we can plug this into the formula to solve for A. So we have 6,500 times E raised to the 0.05 times 6. All right, so now, all right, calculator, type all that into the calculator. We don't even need to do any intermediate calculations. All right, so we've got 6,500 times, let's find our E button. Do you see it? All right, we said there's the log, there's the ln, and the natural log and Euler's number E are inverses. So this E is the second function of the natural log key. So we'll do second e to the x, right? And it automatically gives you e caret parentheses. So we've got 0.05 times 6. Close that parentheses. And we'll get an answer of $8,774.08. That is our accumulated amount when we're compounded continuously. All right, and so we can see a few more examples here. This one was straightforward because we were finding the accumulated amount. All right, what if we were trying to find the principal, or what if we were trying to find the rate, or what if we were trying to find the time? All right, here's an example to where we are trying to find the interest rate needed for an investment of $5,000 to grow to an amount of $6,000 in 3 years if interest is compounded continuously. All right, so identifying our variables. All right, we want the initial investment of $5,000 P to grow to the accumulated amount $6,000 A. And we don't know the interest rate. That's what we're trying to find. And the time is 3 years. All right, so take those numbers, plug them into the formula. 6,000 equals 5,000 times e to the r times 3. All right, here again, you notice that r, the variable that we're trying to solve for, is in the exponent position. Okay, when the variable that we're solving for is in the exponent position, we use that property of logs, to where we take the log of both sides, and that allows us to move the exponent into the front of the log. Okay, but before we do that, we need to get this exponential term, this exponential factor by itself. So the first step is dividing by that number in front, dividing by that 5,000, because the 5,000 is not being raised to the r times 3. It's only the e that's being raised. So we divide both sides by the 5,000. Again, I'm just going to leave the 6,000 divided by 5,000 as it is. Yes, you can simplify that to 6/5. Certainly do that if that makes you more comfortable. All right, now to get the variable out of the exponent position, take the log of both sides, or natural log of both sides, same thing. All right, this allows us to move this 3r to the front of the natural log. That's 3r times the natural log of e. Now, this is why I'm using the natural log as opposed to just a log, because the natural log and the e are inverses, which means that they cancel each other out. The natural log of e is 1. Okay. So in this case, with the continuous compound interest, the natural log is easier because the natural log and the e just cancel out, and you're just left with the exponent 3r. So now the last step is to divide both sides by that 3. And so the rate is natural log of 6,000 divided by 5,000 divided by 3. Okay, let's see what that will be. So we've got the natural log of 6,000 divided by 5,000 divided by 3. This is the interest rate, so we would expect to get a decimal. 0.06077, and at some point you want to round that off. All right, this is our final answer. Certainly out to 5 decimal places is sufficient for this interest rate. Written as a percent, that's 6.077%. That's the interest rate needed to grow that $5,000 to $6,000. All right, so we have one more example that I'll show you with this continuous compound interest. One more example. All right, and this one. How long will it take an investment of $8,000 to double if the investment earns interest at the rate of 8% per year compounded continuously, right? So we're compound continuously. So we're using this A equal P times E to the RT. Identify the variables, right? We're trying to find how long it will take. We want to find T. The rate is 8%, so 0.08. The principal is 8,000. Now they don't give us the accumulated amount. They don't give us A. They only tell us that we want the initial investment to double. Well, if the initial investment is 8,000, then double that would be 16,000. Okay. And it really doesn't matter what that initial principal is. I'll show you what that looks like in the formula. But for now, we'll put the 16,000 equals the 8,000 times e to the 0.08t. Okay. Again, variable is in the exponent position. So what do? We'll first divide by the number in front of that e. And since we're wanting to double, it doesn't matter what that principal is, right? If 16,000 is double the 8,000, this is always going to be 2, no matter what the principal is. So the problem didn't even need to tell us what the principal is, right? It could have just said, how long will it take an investment to double if the investment earns interest at the rate of 8%? Right, then it doesn't matter, right? If it's doubling, then this number is always going to come out to be 2 when you divide the accumulated amount by the principal. So we didn't even need to have that information of 8,000 being the initial investment. Right? We know this is always going to be 2 right there. So we could have just started out our problem in this line. If we're doubling, 2 equals e to the RT. If we were tripling, that would be 3 equals e to the 0.08t. Good. All right, but for now, t is in the exponent position, so we do what? Take the natural log of both sides. And we said the natural log and e are inverses, so what that does essentially is it cancels out the e. I'll still show that step here. But I know that's going to cancel right there, leaving us with just a 0.08t. And then divide both sides by 0.08. And it will always work out like this. If if you want to determine how long it will take an investment to double, it's the natural log of 2 divided by the interest rate. If you wanted to know how long it took to triple, it'd be a natural log of 3 divided by the interest rate. So you can save this work and just jump down to this line if you're comfortable with it. But let's see what that is. Natural log of 2 divided by 0.08. Natural log of 2 divided by 0.08 is 8.66 years. We'll use 2 decimal places here. 8.66 years is how long we would need to invest in order to double our investment.